Hi everybody, today's problem is about the following. Consider these two matrices A and B. They are matrices of 3 by 2, order 3 by 2, and we want to prove is that A and B are row equivalent matrices, and we would like to find a sequence of elementary row operations in such a way that we can produce A from B. And the second part of this problem is to find an invertible matrix M such that B is a product of M times A. So let's go to the solution of our problem. So we will write our matrix B in green, and we would like to apply the first row operation. So there are several possibilities here, and then you have to choose one that you think that is getting closer to the matrix, getting you closer to the matrix A. So for example, I choose this one. So 2 times row 2 plus row 1. So you have to realize that with this notation, I'm meaning that I'm going to multiply row 2 by 2. So I'm using row 2 to modify row 1. So then the row that I'm changing here is the row 1. So knowing that, I start to perform my operations. So you see that after multiplying by 2 the row 2 and adding to the row 1, you start to get this sequence of numbers: 2 minus 1, 2, and 0. Then the rest of the matrix remains the same, and then we have to perform another row operation. The next row operation that we are going to perform is dividing by 3 the row 3. So you see that clearly that if you divide by 3 row 3, then you are getting in fact these little numbers, so 1, 0, 1, and minus 1 of row A. So dividing by 3, we get the first the 1, 0, 1, and minus 1. Now, next step, we are going to apply this row operation. So we are going to exchange or interchange row 3 with row 2. If we apply these operations, so we clearly see that the matrix that I get is matrix A. So with this sequence of row elementary operations, we are proving that in fact A and B are row equivalent, and we have the sequence of elementary row operations that give me in fact the solution of my problem A. Now, to solve my problem B, my part B, we have to work as follows. So let's erase this part and let me write again the sentence of the problem at the top of the page. So that's it. So we see that the row operation that I am performing here is equivalent to multiply by the left by the elementary matrix corresponding to the row operation. So in parentheses, I'm writing, or I'm meaning, the elementary matrix associated to the row operation. Remember that an elementary matrix is the matrix resulting after applying this elementary row operation to the identity. So applying a row elementary operation is equivalent to multiply by the left my matrix, okay, by this elementary matrix. So since I applied first this operation, then I multiply first by this operation. But the second operation that I have is multiplying by 1/3 row 3. Therefore, I have to multiply by the left by 1/3 row 3, but the elementary matrix attached to this row operation, and so on. So at the end, we perform the exchange of row 2 and row 3, so I multiply by the left by the matrix that exchanged row 2 and row 3. So what we have produced now is a product of 3 matrices, okay, that are invertible. Each one is invertible, therefore the product is invertible. And of course, the product of these 3 matrices and B gives you the matrix A. But remember that our problem is to express B as M times A. So what we can do is basically isolate my matrix B from the previous row. And how do I isolate? Multiplying by the inverse matrices. So you know that if you want to invert, or you want to find the inverse of this product of the matrices, is the product of the inverses of the matrices, but in the other way around. Okay, in the opposite order. So in this way, we have expressed my matrix B as a product of big matrices in red and the matrix A. So now the only thing that we have to find is the inverse of these elementary matrices. So this is very easy. The inverse of 2 times row 2 plus row 3 is minus 2 times row 2 plus row 1. Sorry, is row 1. And then the inverse of 1/3 of row 3 is 3 times row 3. And the inverse of the permutation matrix that changes the row 2 and row 3 is exactly the same. So guess what? The matrix that we are looking for, therefore, is this M. So just let's be explicit and let's calculate the matrix M. So if I write the multiplication of these three matrices, so remember, just take a look. Minus 2 row 2 plus row 1 should be this elementary matrix. This is the elementary matrix that is a result of applying this elementary operation to the identity. So we get this one and so on. Okay. And then since the product of matrices is associative, we can choose, or I choose to first realize this operation. So if I perform the multiplication of these two matrices, I get as a result this one. Therefore, I write my third matrix at the side, and I perform the multiplication to get my final answer. So my matrix M is this matrix: 1 0 minus 2 0 0 1 0 3 0. So basically, this is the end of the problem, except that always a good idea to verify our results. And the best idea, or the best way that we have so far to verify that our result is correct, is actually doing the calculation that we supposed to. So if what happens if we multiply the matrix M by A, I would like to obtain the matrix A, and then if I perform the operations, you see that in fact our result is as expected. Okay, so next problem is to calculate the determinant of the matrix formed by A and B's, in which you have mostly everywhere B's, and in the diagonal you have A. So there are several ways to calculate it, but so far the only techniques that we know to calculate it is using elementary operations, okay, and maybe cofactors, but you don't want to use cofactors. So let's use elementary operations to do this. So we are going to use a combination of row reduction and column reduction, okay. So, and the final idea is to get a triangular matrix. And you know that if you have a triangular matrix, the determinant of a triangular matrix is just the product of the elements in the diagonal. So our objective will be to use these column and row operations to my matrix in order to get a triangular matrix and then apply the theorem. So the first thing that we are going to do is do minus 1 row 2 plus row 3, and this implies that we are modifying row 3, and this other operation minus row 2 plus row 4, and this means that we are using row 2 to modify the row 4, so we are changing row 4. So we write our matrix. So once we do the first elementary operation, minus 1 row 2 plus row 3, so we have to perform the minus 1 B plus B, so that gives me the 0 I just wrote here. So minus 1A plus B is B minus A, so the next entry is B minus A, and then we get A minus B, because this is minus 1 times B plus A, so that gives me A minus B, and finally B minus B will be 0. And if we perform the operations for the second elementary operations we are applying is minus 1 row 2 plus row 4. We get easily that we get 0, b minus a, 0, and a minus b. So we are getting close to a triangular matrix, but still we have some work to do. So the next operation that I'm going to do is not a row operation, but it's a column operation. So I'm multiplying 1 times column 4 plus column 2. Why I'm doing this? Because I see that in the last entry of column 4 I have the negative of the last entry of the column 2. Therefore, if I add them, I can make 0 this part here. So I'm performing this operation, and we see we erase second column, which is the one that we are modifying, and the first entry will be 2b because we are adding b plus b, and then we are adding b plus a, then b minus a plus 0 remains b minus a, and then b minus a plus a minus b is 0. So we get this matrix. Very good. So we have to continue. Now remember that we want to do this triangular matrix. So the next column operation that I choose to do is 1 times column 3 plus column 2. And why I'm doing that is because I have this term here that I can use to eliminate this term here, and since I have a 0 here, this 0 is not modifying this entry. So if we perform these operations very fast, erase my second column, and once again I see that the first entry should be 3b because we are adding 2b plus b, then will be a plus 2b, 0 and 0. So in fact we are very close. So the only problem here is this b, how to eliminate this b. So there are several ways to do it, but I am doing an intermediate step just to work all the time with the I don't like to write with fractions. I don't like to work with fractions, so I perform this operation first. Is minus 1 row 1 plus row 2. So minus 1 row 1 plus row 2, so I'm modifying row 2 using row 1. So I am subtracting row 2 minus row 1. So I will get b minus a in my first entry. So let me write the matrix. Let me do this. So it's b minus a in the first entry. So a plus 2b minus 3b, which is for the second, will give me a minus b. And then I get 0 and 0 because I'm subtracting b and b. Okay? So that's very nice because now you see once again that a minus b and b minus a, one is the negative of the other. So if we want to erase this part, since I have zeros here, so I can use the second row to erase this term here. So this is what I am doing. So 1 times row 2, 1 time column 2 plus column 1 once again. And very fast, let me write the matrix and erase whatever I need to erase, which is column 1, and then using this to modify it. So I get a plus 3b because we are adding this guy and this guy. Next term is 0, this is what we wanted, and then the remaining terms is 0. So now I get a triangular matrix. So you know that the determinant of a triangular matrix is the product of the elements of the diagonal. So I have 3 times a minus b and 1 time a plus 3b. So it's a minus b to the power 3 times a plus 3b. So the determinant of my matrix that I was looking for is a minus b to the cube times a plus 3b. And that's it. Thank you very much for watching, and see you next time.